So there are two different things that we use integration for. The first is to reverse differentiation. So if we've been given a derivative, we can find out what the original equation would have been. And we do that obviously by the rules of integration. So we'd get our function y equals some stuff. And then there could have been numerical terms that when we differentiated disappeared. And so when we integrate, we need to remember to add them back in, or at least add the possibility of them back in. And that's why we add in r plus c. Now, if we're not integrating a derivative and we're integrating a function, what that does is it finds the area underneath the curve. So it will take whatever shape our thing is and tell us about how much area is underneath that curve. So for a general term then, ax to the n, that we integrate, we will end up with a over n plus 1, x to the power of n plus 1, with our constant of integration, assuming that we need it. So let's do a quick example here. Now, to integrate this expression that we've got in our question here, we're all good for the first term. The second term is not so nice as it is. So much like with differentiation, we're going to change that to a index expression, so x to the power of a half, and then we'll integrate 1/4 x to the power of 4, so add 1 to the power, divide by the new power. This will become x to the 3 over 2, and so 2/3, minus our 3x, and add c. Now we're told that the curve passes through the point 1, 5. The moment it tells you anything like that, it's basically screaming at you, find your plus c. Because now we know a value for y and a value for x, 1 and 5 over 2. We can chuck all of our values in. So we'd say 5 over 2 equals 1/4 of 1 to the power of 4 plus 2/3 of 1 minus 3 lots of 1 plus c, and rearrange for c. You must then write your equation out in full at the end. That's the final mark. So you've got to make sure that you have done that at the end. The way the exam is going to get tricky is if they give you these kind of compound areas under curves. So the integration bit is fine, but when you are trying to kind of find these total areas, you're going to have to get crafty about how you figure things out. Nearly always a couple of lines kind of helps you out. So here, in this first example, if I draw a line straight down from where these two lines cross, I can see that the first part of the area is the area underneath this actual curve, up to whatever the point is where they intersect. And then the second area is either the area of a triangle, or maybe this isn't a straight line, here it's another curve, but you can see then that it's the area underneath this second curve between two other points. So some key points you might want to work out here. Well, we know that this is x equals 0. What about this one here? And of course that's where these two curves intersect. And what about this one? Well, that's where the second curve has y equals 0. So you will need to go away and do some coordinate geometry, perhaps simultaneous equations, that kind of stuff, to find those key points. But you can see that the actual areas are now a little bit more straightforward. And the other thing they can do is trap an area explicitly between two curves, and you get this kind of lozenge shape or something equivalent like that. You can see that there's a really key point here where the two lines cross. Now, so we've got our or wherever they cross, it could have been 2 points here, but one of them, it appears, is on our where x equals 0 there. What we would do to calculate this is take the larger of the two areas, so that's the area of the curve across the top, and that produces this larger area that I'm shading in yellow here, and then subtract the area of the underneath the bottom curve, so the lower curve. In essence, what you're doing there is taking the integral of the top curve minus the bottom curve. And you can do that algebra before you start integrating if you want. If both of those techniques fail, so you've tried simultaneous equations, found crossing points, tried adding and subtracting areas, look for standard shapes. So here, if I draw a line straight down from this point, I can see that I actually have a triangle here. So it's quite possible that this area, which I can call A, is made up of the area underneath the curve, between 0 and this point over here, and then minus the area of the triangle. In all of these situations, my one piece of advice for the exam would be to write out what you intend to do. And then that way, even if it goes wrong, as long as it's a correct method, even if you screw up your integration and everything else goes, absolutely wrong, you should pick up your method mark for your process. So even if it's just little pictures like do area A plus area B, or do, big lozenge shape minus other shape, just something that shows your examiner that you're going to try and find two separate areas. If you do some simultaneous equations, it can really help to just write simultaneous equations, ... and then do them. Basically, you want to give your examiner as much opportunity as possible to follow what you're doing. And that's it.